In this video, I will show you how to evaluate integrals using your graphing calculator. Along the way, I will also show you how to use the first fundamental theorem of calculus to solve problems. In the setup, we are told that g prime equals 10 minus e to the radical x power, and we are given that g at 0 equals 2. For part A, we first must find the integral from 0 to 4 of g prime dx. Let's use our graphing calculator to find this. I am going to show you two different ways to do this, and you can decide, depending on the circumstances, which method you want to use. First of all, you can just come to a blank screen and set up your integral. You're going to hit the math button, and option number 9 is an integral. So I like to just hit the 9 button. So we're ready to go. We are integrating from 0 to 4. So I'm going to put a 0 right here, and then I'm going to come up here and put a 4. And then in the main part, this is where you type in the function. So let's look back and see what that thing was again. We are integrating g prime, and g prime is 10 minus e to the radical x power. So that's what we put in, 10 minus e to the radical x power, and of course dx. So guess what? You just hit enter and kabam! This is the value of the integral. On the AP exam, they will accept two versions of this answer. Your answer must be accurate to 3 decimal places, and you can either truncate or round. So we can write 23.221, all right, just sort of cutting it off right there. Or we can round and write 23.222. Either will be accepted. Free response questions on the AP exam always come in multiple parts, and sometimes an answer that you found in part A will be needed in a later part. So it's a good idea to save your answer and store it on your calculator. So if I hit the store button, I can assign this entire decimal to a letter. I'm just going to use the letter A. So if I do alpha A and enter, I have now stored this entire decimal. That's important because if I need this number later, it will not be good enough to use 23.221 or 23.222. To avoid a rounding error that would cost me a point on the AP exam, if I need this value again later, I need to use the entire number. And by storing this value into the letter A, if I need this value again, I can just pull up the letter A, and I am actually using the entire number, not some rounded version. Here is the other way to evaluate an integral. You can hit the y equals button, and here you can type in the function that you want to integrate. There's a system that I like to use, and you can borrow this if you want. If I have an original function, I always put it in y1. If I have a derivative, I put it in y2. And if I have a second derivative, I put it in y3. That way, it's easier for me to remember which function is which. So in this case, I'm typing in g prime. This is a derivative, so I'm going to put it in y2. So I'm going to type in 10 minus e to the radical x right now. So here I go, 10 minus e to the radical x. Quit your way out of this screen by hitting second quit, and use the math button to access the integral function like we did before. So let's go ahead and just type 9, and again we are integrating from 0 to 4. But this time, instead of typing in the function here, we can refer back to the function that we typed into y2. We do that by using the vars button. Hit vars and then shift over to the yvars tab, and then just hit enter because we want the function. And our function is in y2, so just grab that. So y2 here represents whatever you typed into y2. So, and of course we are doing with respect to x. And of course you get the same answer you got the last time. The reason why this is useful is because if we need to use this function again later for any reason, it's right here in y2. We won't have to type it in again and again. And this function is fairly simple, but sometimes these functions get very complicated and time-consuming to type in repeatedly. So sometimes it can be quite a time saver to just put the function on one of these y1, y2, or y3 and refer back to it instead of typing it in repeatedly. Here is the second half of part A. Explain how this is related to, but not the same as, the value of g at 4. To answer this question, we will refer back to the first fundamental theorem of calculus, which is what we use every time we evaluate a definite integral. So, you know how we always say, okay, we find the antiderivative, and then we evaluate the antiderivative from a to b. But in order to evaluate this antiderivative, we find the value at b, and we subtract the value at a. In other words, the integral of f of x from a to b equals the antiderivative at b minus the antiderivative at a. So this is one version of the first fundamental theorem of calculus. However, the integral of f prime is just f. So when we evaluate the definite integral, we get f at b minus f at a. So this is another version of the first fundamental theorem of calculus. Remember that f prime represents a rate. So we are taking the integral of a rate from a to b, and then we are getting these values. Specifically, we get the difference in value from a to b, or the change in value from a to b. So we can translate the meaning of the first fundamental theorem of calculus into words by saying the integral of a rate from a to b is equal to the net change in value from a to b. So from now on, anytime you see the integral of a derivative from a to b, I want you to think, oh, that's the net change in value from a to b. But that's exactly what we have here. The integral of g prime from 0 to 4 is the net change in the value of g from 0 to 4. So how does this compare to g at 4? We could say that the integral of g prime from 0 to 4 is the net change in the value of g of x from 0 to 4, while g at 4 is the value at 4. For part B, we need to find the value of g at 4. We can use the first fundamental theorem of calculus to do this, but let's rewrite this a little bit. If we add f at a to both sides of the equation to get f at b by itself, we get f at b equals f at a plus the integral of f prime from a to b. In other words, the end value equals the initial value plus the net change in value from a to b. Looking back at this problem, we have the integral of g prime from 0 to 4. This represents the net change in the value of g from 0 to 4. That means that g at 4 is the end value, and g at 0, okay, we're going from 0 to 4, so g at 0 is the initial value. And according to our first fundamental theorem of calculus, the end value will equal the initial value plus this integral. In the setup, we were given that g at 0 is equal to 2, so we can substitute 2 for g at 0 right here. In part A, we found that the value of the integral is 23.222, so we can make that substitution here. So g at 4 equals 2 plus 23.222, which equals 25.222. Part C, find g prime at 4. Remember that we were given g prime equals 10 minus e to the radical x. So that means g prime at 4 will equal 10 minus e to the radical 4. Of course, the square root of 4 is 2, so we get this. These are acceptable answers for a free response question. However, we do have access to a calculator, so maybe let's go ahead and write the decimal as well. I could certainly just type in 10 minus e squared, so I get this answer, 2.611, or they would accept 2.610. That was easy enough, but since we have the function typed into y2, another thing that we could do is do second table, and notice you see that y2 is sitting right there. If I type in an x value, then I can evaluate any function at that particular x value. So right now I'm evaluating at x equals 4, and there you go, 2.611. Part D, find g double prime at 4. Since this is a calculator active problem, the most efficient way to find g double prime at 4 is to take the derivative of g prime and evaluate that at x equals 4. So remember, we have g prime typed into y2. So the quickest thing to do is to hit the math button, and this time we want to take the derivative. So I'm going to use function 8, and we are doing the derivative with respect to x of g prime. So I'm going to put y2 right here because y2 represents g prime. And we do that by hitting vars and switching over to y vars. We will hit enter for function, and then there's y2. So there we go, we're taking the derivative of y2, the derivative of g prime. And we are evaluating at x equals 4. So this is the answer. And there's really no work to show, you can just write the answer. If you didn't want to use the shortcut of typing the equation into y2, and maybe this whole business of using vars and y vars, maybe that feels like it's too many steps. So instead, you could just type the math button and hit number 8 for derivative. So we're taking the derivative with respect to x, and right here you can just type in the entire function. So g prime was 10 minus e to the radical x power. And then we can evaluate that at x equals 4. Alright, so you can get the same answer this way. Of course, if you really have a lot of time on your hands, you can find g double prime by hand. So we are given that g prime is equal to 10 minus e to the radical x. I'm going to think of it as 10 minus e to the x to the 1/2 power. We can find g double prime by taking the derivative of g prime. Of course, the derivative of 10 is 0, so that's gone. I'm going to bring down this negative sign. So I'm about to do the chain rule. So the derivative of e to the something is still e to the something. So I start by writing e to the x to the 1/2 power. But then, because it's not just an x, I need to multiply by the derivative of this inner function. So I need to multiply by the derivative of this. The derivative of x to the 1/2 power is 1/2 times x to the negative 1/2 power. Let's simplify this down a little bit. I see the negative sign in front, so kabam. I see the 1/2 right here, so let's put a big old 1/2 in place. In the numerator will remain my e to the x to the 1/2 power. I'm going to put this back as e to the radical x again. And then I have this x to the negative 1/2 power. The negative exponent means it will end up in the denominator. And then I will put x to the 1/2 power as the square root of x again. And we don't need the 1 at this point. So if I want to find g double prime at 4, I'm just plugging in 4 for each of these values, each of these x's. So I will have g double prime at 4 is equal to negative e to the square root of 4 divided by 2 times the square root of 4. Of course, the square root of 4 is 2. So I will have g double prime at 4 is equal to negative e squared over, and this is just 2 times 2, which is 4. Just because you have access to a calculator doesn't mean that you have to put your answer as a decimal. You can write an exact answer like this, but I will consider this the long way since we did have a calculator. Part E. The graph of g has exactly one horizontal tangent line. Find its x-coordinate. Long ago, we learned that the graph of g will have a horizontal tangent line when g prime is equal to 0. This is a calculator active problem, so the most efficient way to find where g prime is equal to 0 is to use the graphing calculator. Remember that we typed g prime into y2. So let's hit graph and take a look. We want to know where g prime is equal to 0. We can estimate, this is 1, 2, 3, 4, 5, it's 5 point something, maybe 5.3, something around like that. Obviously we want 3 decimal place accuracy, so how do we find it? We will hit second trace, and one of the options is 0, so that's we're finding where the function equals 0. I'm just going to hit 2, and now it is asking me for the left bound, so I'm going to use my arrow key to move the pointer to the left of the intersection point, and I hit enter. Now the software asks me for the right bound, so I'm going to arrow over to the right until I am definitely to the right of the x-intercept, and I will hit enter. So now I will arrow my way back very close to approximately where the function is 0, and I hit enter. So I get this answer, 5.302, or truncated 5.301. G of x has a horizontal tangent line at x equals 5.302. Back to the calculator. If you thought you might need this value again for another part later, you could save this value into a letter on your calculator. Just quit by hitting second quit, and immediately hit the store button and choose the letter you want to store the value into. So I'm going to use alpha B. So I have stored this entire number into the letter B. So if I need this number again, this is what I will use instead of using 5.302, because that would give me a rounding error that could cost me a point. Now, I know what you're thinking. That was way too fast. Is there a way that we could do it that's like maybe 5 times as long? Sure, we could solve this by hand. So let's set this equal to 0 and solve. So 10 minus e to the radical x is equal to 0. This should give us the location of a horizontal tangent line. Let's add e to the radical x to both sides of the equation. So we get 10 equals e to the radical x. I could get rid of this e by taking the natural log of both sides of the equation. So I would have the natural log of 10 is equal to the natural log of e to the radical x. Natural log and base e are inverse functions. They cancel each other out. So on the right-hand side, I'm just going to have radical x. On the left-hand side, I still have the natural log of 10. To free the x from this radical, I am going to square both sides. So that is going to give me the natural log of 10 squared is equal to x. So guess what? This is an exact answer to the question. Natural log of 10 squared. Just for fun, let's check it on the graphing calculator. So if I take the natural log of 10 and I square it, I get 5.302. Part F. At the x-coordinate you found above, does g have a relative minimum, a relative maximum, or neither? Justify your answer. We have learned two ways to identify a relative max or a relative min. One is the first derivative test, and the other is the second derivative test. Let's start with the first derivative test. This is where we make a sign chart of g prime. If I were doing this by hand, I would pick a test value to the left of 5.302. For example, if I put in 0, then that would be e to the 0, which would be 1. And then 10 minus 1 is 9, which is positive. So I have positive values over here. And then if I pick values that are bigger than 5.302, like say if I do e to the 10th power, well, that's a really big number, so 10 minus that will definitely be negative. And then I could see that the first derivative is going from positive to negative, which indicates that we have a relative maximum. Kabam! Since we do have access to a graphing calculator for this problem, I need to point out to you that if you simply graph g prime, you're looking at a sign chart. So here's the 5.302. To the left, it's positive. To the right, g prime is negative. So we can see that g prime is going from positive to negative, and therefore we have a relative max at 5.302. So we would say g of x has a relative max at x equals 5.302 because g prime changes from positive to negative at x equals 5.302. And that's your first derivative test. But we could also use the second derivative test to identify relative extrema. If I want to know if we have a relative min, a relative max, or neither at 5.302, I evaluate the second derivative at 5.302. Of course, the fastest way to evaluate g double prime at 5.302 is to use your graphing calculator using all of the tips and tricks I've taught you throughout this video. For example, remember that I stored the value 5.302, etc. into the letter b. So the letter b contains this entire number, not a rounded value. So keep that in mind. Also remember that I typed the function g prime into y2. So if I want to find g double prime, I want to find the derivative of y2. So I can just go to a blank area on my calculator. I'm going to hit the math button, and I want to take the derivative. So that's option 8. So derivative with respect to x, and I want to take the derivative of g prime. I could type in g prime right now, but it will be faster if I do vars, y vars, and pick y2. So this is the derivative of g prime. And I want to evaluate this at 5.302, but I don't want to round like that because that will cause a rounding error that could cost me a point. So instead, I will use the letter b, which contains all of those good decimals. Kabam! So this is the answer, and that is by far the fastest way to come up with this answer. Okay, I shouldn't say that's the answer because we are trying to determine if we have a relative max, a relative min, or neither. What matters is that g double prime at 5.302 is negative. It is less than 0. The fact that g double prime is negative indicates that the original function is concave down in this vicinity, which means that any horizontal tangent line will occur at a relative maximum. When you write your summary and justification for the second derivative test, it has to be written in a very specific way. We will say g of x has a relative max at x equals 5.302 because, and you must say two things here. The first part is that you must say that g prime at 5.302 is equal to 0. And now here comes the second derivative. G double prime at 5.302 is less than 0. Again, when you use the second derivative test to identify a relative max or a relative min, make sure your justification includes both of these parts. What if I want to use my graphing calculator to help me with the second derivative test, but I'm not really comfortable with all of the tricks and shortcuts? I didn't store the value into letter B. I didn't type G prime into Y2. I'm not comfortable with using vars and Y-vars and all of that. Is there a way that I could still use my graphing calculator to evaluate the second derivative at 5.302? Yes, there is. So let me show you what you would have to do. It's just will take a little bit more typing, but you understand that if we were finding the second derivative, I'm taking the derivative of the derivative. So you know I need to take the derivative. So hit your math button and use option 8. Now we're taking the derivative. We're taking the derivative of g prime. If we don't want to use y-vars and all that, I can just type in g prime right now. And g prime was 10 minus e to the radical x. So that's e to the radical x. Okay, so this is the derivative of g prime. So this will be g double prime. And now I want to evaluate it at 5.302. However, if I did not store the value in a letter earlier, then I need more decimals. Actually, since all we care about is whether the result is positive or negative, we can probably get away with 5.302. So this would be enough to tell that we have a negative value.